So let us generalize this. Here we have an m by n matrix, m rows, n columns. Okay? And again, we can take the first column, put it in memory first, then go to the second column, put it in memory second, and so forth. All right. Now what happens now? What happens now is that if A is the address where the first element is stored, then we would address that with A of 0. The next one would be A1, etc. And therefore the last entry in the first column would be A of m minus 1. And then the first entry in the second column would go to A addressed at m, and so forth. So these would all be contiguously stored in memory in this way. First column, second column, third column, and so forth. Now if you look at this carefully, notice that this is A of 0 times m plus 0. That evaluates to 0. The next one is A 0 times m plus 1. This index is the same as that. The last one in the first column would be A of 0 times m plus m minus 1. Okay. And then the first entry in the second column would become A of, now you've already stored m entries, so you would get 1 times m plus 0. You notice that this corresponds to that, and this corresponds to that. And what we're starting to see here is a formula for how to find a particular entry in the matrix. Okay? If we have a general entry alpha I comma j, then we see that that's stored at A of j times m plus I. And now if you go back to the launch, there we defined these macros that translated the ij entry in a matrix to the actual location where it's stored, and this explains how that worked. But there's actually a slight twist which we're going to see in the next unit, and that's known as the leading dimension of a matrix. First, go and do some exercises.